We're going to start here by looking at the derivative for some function y of x. Now here's our function. It's a curve that moves along here. Y is a function of x. And the first derivative is the slope, or the gradient, or the rate of change of y as we change x. Now what we imagine is that we're going to make some small change in x, which we'll call dx, and as a result we're going to get some small change in y near some point, for example here, and we're going to define that ratio as the derivative. And we can write it with this notation with the little prime in here, the little superscript prime, or we can write it with this ratio notation, and that ratio notation is called Leibniz notation. So let's look a little bit more closely at the first derivative round about some specific point. So we'll think about this point x1. We've got a region around here. I've sketched a dashed line here. And a notation we're going to use at this part here is to say that this derivative at the point x1 we can also write in the Leibniz notation by putting a line on the right hand side and marking x1 down at the bottom. We will also use that notation for something different later on, so this notation is a little ambiguous. The derivative, the value of it, is the slope of this tangent line. That's the one that just touches the curve at this point and is parallel to it when it touches it. And it is mathematically equal, the slope, to this tangent, delta y over delta x. We could look at some other point over here. We would have a different value of dy by dx. In this case, the slope is obviously going in the other direction, for example. So let's look more closely at the first derivative, and let's define what we mean by that. So what we're going to do for the moment is we're not going to start out by looking at the slope of the black line here, but we're going to look at the slope of this upper line, this orange line. And we can write down what that slope is. So the change in y as we go from this point to that point, well, we can write down what that is mathematically. This point here is the point x minus delta x over 2, so x1 minus delta x over 2. And this point here is the point x1 plus delta x over 2. So by definition, the value of y at this point is y of x1 plus delta x over 2. That's just what we mean by y of x. And similarly down here, the value of y is the value y of x1 minus delta x over 2. We're sort of going halfway in both directions here. So these are just, by definition, that's what we mean by the function y of x. And so the height here of this portion is just this number minus this number. So that's our delta y, and our delta x, of course, is just whatever we chose it to be. So the slope of this orange line, this upper line here on the curve, is by definition delta y, that's the difference in the values of y, divided by the difference in values of x. This is delta y over delta x. That's the slope of the orange line. Now, let's look at what happens here as we reduce the size of delta x. We've reduced the size of delta x here, and you can see what is happening is that the orange line, the upper one of this pair, is getting closer and closer to the black line. And we're saying, therefore, that this orange tangent line is becoming closer to the slope of the black tangent line. So what we say is that in the limit, as we make delta x very small, in fact, we say in the limit as delta x tends to 0, and that's how you read this symbol here. When you see that, you see that's the limit as delta x tends to 0. We're not saying it becomes 0, we're just saying it becomes as small as you like, as close as you like to 0. Then this ratio that we've written down here becomes the first derivative. So we're saying that dy by dx at the point x1 is the limit as delta x tends to 0 of the change in y over the change delta x in x. Now let's look at the sign that we get for first derivatives. On our curve here again, if y increases as we increase x, so that's what happens here at our point x1, then dy by dx is greater than 0 because we've had a positive delta x in going from the left to the right, and we've got a positive delta y in going upwards here correspondingly in y. So dy by dx is greater than 0 for this particular example. We're sloping up to the right, and that means dy by dx is greater than 0. If y decreases as we increase x, which is what we see over here at our point x3, then dy by dx is less than 0 because y has decreased as x has increased. And here we're sloping down to the right. So when we're sloping down to the right, the derivative dy by dx is less than 0. Now let's look at some standard derivatives. I'm not going to work these out for you. I'm just going to state what the results are. So the derivative of a power, that is x to the power n, is n times x to the power n minus 1. So let's just look at that. Here's a curve, y equals x squared, a simple parabola. And the derivative of that curve, well, according to this formula here, it should be 2x. X squared goes down to x to the power 1, and we take this n here to become a multiplier in front. So dy by dx is equal to 2x, and that is just a straight line that goes through the origin. And what that is saying is that the slope starts negative here and gets progressively smaller, actually exactly proportionately smaller, as we move down towards the origin, and then it gets proportionately larger as we move into the positive x territory. The derivative of a straight line, here's a straight line, so that's x to the power 1, is just a constant. So we've taken x to the power 1 and turned it into x to the power 0 by taking the derivative, and that, of course, is just a constant. And this is true for any straight line that comes to a constant. What the constant is depends on the slope of the straight line, of course. So the straight line here has a constant slope, so it has a constant derivative. The derivative of a function does not depend on the overall height of the function. So all these lines here have the same slope. This one, which we've moved up a little bit, has exactly the same derivative because the derivative of a constant is just 0. There's nothing changing. And again, as we go up to x plus 0.5, we've just moved the line up, the derivative remains exactly the same. The derivative of a constant, here's a line that is just a constant, y equals 0.5, is of course just 0. There's no rate of change of y with x, so the derivative is 0. One very important function, of course, that we come across again and again is the exponential, and the derivative of an exponential is just the same exponential, e to the x. The derivative of that is e to the x. So this is a remarkable property, and is actually one of the reasons why we like to work with logarithms and exponents of the number e, or to the base e. So here's the function y equals e to the x on the left-hand side. And here's its derivative. It's exactly the same function. And this is the only non-zero function for which that is true. The derivative of the logarithm is also a very important derivative to know. The derivative of the natural logarithm of x is 1 over x. Again, this is a reason why we like to work with natural logarithms. Any other logarithm in here will have some constant on the right involved with it. So here is, again, plotted the function y equals log of x. And on the right-hand side, we see the derivative. And you note, of course, the derivative is also exploding at the origin. It's also becoming infinite. It's this hyperbolic reciprocal function here, is a reciprocal or an example of a hyperbola. And that also corresponds with the fact the function itself is becoming infinitely large and negative as we head down towards 0. The derivative is also becoming infinitely large, in this case positive. Derivatives of sine and cosine. The derivative of the sine is the cosine, which is easy to remember. And again, we can remember that by remembering the form of the sine curve here. It is going negative here, and it's got a negative slope. It turns around and has a positive slope. And then here it has a positive slope and turns around and has a negative slope. So that's what the cosine curve looks like. Here it's got a negative value, so that corresponds to this negative slope. Here it has a positive value corresponding to this positive slope. Here it has a positive value corresponding to this positive slope. And here it has a negative value corresponding to this negative slope. The derivative of the cosine is minus the sine. Here's our cosine function again. And we see that we have a positive slope here, which is a positive value on this curve, which is minus sine of x. Sine of x itself would be a curve that looks like this. The slope is positive in here, and we see that we've still got a positive slope here. The slope is negative here. We see we've got a negative value here. It continues negative here. We've still got a negative value there. So the derivative of cosine is minus sine.